Somewhere, right now, as you settle into the quiet of this moment, there is a fact about your existence that almost no one has told you. You are inside a hole, not a hole in the ground, not a hole in a wall, a hole in space itself, 2 billion light years wide, confirmed by 3 astronomers in 2013, and so vast that it contains our entire galaxy, our sun, our planet, and everything within 1 billion light years of us in every direction. The matter that should fill this region, the galaxies, the clusters, the threads of cosmic structure that stitch the universe together, 20% of it is simply missing. And that absence, that quiet, enormous emptiness, is warping every measurement we have ever made about the cosmos. It is bending our understanding of how fast the universe expands. It is threatening our calculations of how old the universe is. It may be distorting our grasp of reality itself. Close your eyes for a moment if you like. Let the weight of that settle. You are not on solid ground in the way you imagined. You are drifting through a desert of space so immense that light itself takes 2 billion years to cross it. And the universe you think you know may look nothing like what it actually is. Welcome. I am so glad you are here tonight. Whether you are lying in the dark, driving through the quiet hours, or simply looking for something to carry you gently through this evening, I want you to know that this space is yours. There is nothing you need to do, nothing you need to solve. Just listen and let the cosmos unfold around you, one question at a time. Tonight, we are going to explore one of the most unsettling discoveries in modern science. The discovery that we live inside a cosmic void, a region of space so underdense and so enormous that its very existence challenges the foundations of cosmology. We will ask how it was found, what it means, why it matters, and what it reveals about the nature of reality. Along the way, we will encounter frozen sound waves from the infant universe, galaxies rushing through space at 600,000 miles per hour, and a crisis in physics that has no clean resolution. Before we begin, a gentle moment. If these quiet explorations help you find rest, or wonder, or simply a few hours of peace, a gentle like or a quiet tap on subscribe would mean the world to me. Every bit of your support keeps this tiny corner of the universe alive and helps others find their way here too. One sleepy soul at a time. Thank you, truly. Now, let us begin with a question that changed everything. Part 1. What happens when you count the galaxies and the numbers are wrong? In 2013, 3 astronomers set out to do something that sounds almost routine. Ryan Keenan, Amy Barger, and Lennox Cowie wanted to map the distribution of galaxies in our cosmic neighborhood. They gathered data from multiple galaxy surveys, compiling the positions and distances of roughly 35,000 galaxies spread across billions of light years of space. The goal was straightforward: map the galaxies, measure their density, compare the results to the predictions of the standard cosmological model. The standard model, known as lambda cold dark matter, or lambda CDM, has been one of the most successful scientific frameworks in history. It explains the faint afterglow of the Big Bang, a sea of microwave radiation that fills the entire sky. It accounts for the relative abundances of hydrogen, helium, and lithium created in the first few minutes of the universe's existence. It predicts, with remarkable accuracy, the way galaxies cluster together into filaments and sheets separated by enormous voids. As NASA's Goddard Space Flight Center describes it, lambda CDM is the simplest model that provides a reasonably good account of the properties of the cosmos, including the existence and structure of the cosmic microwave background, the large-scale structure of galaxy distribution, the abundances of the lightest elements, and the accelerating expansion of the universe, One of Lambda CDM's most fundamental predictions is that the universe should be roughly homogeneous on the largest scales. Zoom out far enough, past individual galaxies, past clusters of galaxies, past even the great walls and filaments of the cosmic web, and the density of matter should converge toward the cosmic average. Some regions will be denser, some will be sparser, but averaged over volumes of a few 100 million light-years, the variations should be small. Keenan, Barger, and Cowie expected to confirm this prediction. They did not. Everywhere they looked near Earth, there were fewer galaxies than there should have been. The deficit was not small. It was 20%, and it was not confined to a narrow slice of the sky or a single direction. It extended outward in every direction for approximately 1 billion light-years, forming a vast spherical region of cosmic emptiness with our galaxy disturbingly close to the center. This was not a typical void, the kind of modest underdensity that sits between galaxy clusters and is easily explained by standard structure formation. This was a void on a scale that the standard model struggles to produce. 2 billion light-years across, 20% below cosmic average density, centered more or less on us. The researchers checked their work with the rigor that extraordinary claims demand. They used multiple independent galaxy surveys. They examined the sky from different angles, employed different distance estimation techniques, and controlled for known systematic biases. The result held. The signal was consistent, robust, and deeply troubling. As Keenan later explained to colleagues, the data left little room for alternative interpretation. The void was real. They named it after their own initials, the KBC void. 3 letters that sound almost casual, but there is nothing casual about what those letters represent. To appreciate why the KBC void disturbed the astronomical community so profoundly, consider what the standard model says about the likelihood of such a structure existing. Computer simulations of the universe's evolution, starting from the initial conditions encoded in the cosmic microwave background and running forward through 13.8 billion years of gravitational collapse, rarely produce voids this large and this deep. When researchers run thousands of simulated universes, the vast majority contain no structure matching the KBC void's size and density deficit. Some analyses have calculated the statistical probability at less than 1 in 1,000. Others have placed the void at a 10 sigma deviation from the expected density. To put that in perspective, a 5 sigma result in physics is considered the gold standard for discovery. It means there is less than a 1 in 3.5 million chance that the result is a random fluctuation. It is the threshold that was used to confirm the existence of the Higgs boson at CERN in 2012. A 10 sigma result is so far beyond that threshold that the probability becomes essentially incalculable in practical terms. You would need to survey volumes of space containing trillions upon trillions of potential void locations to expect to find even one example. And yet, here we are, living inside one. As the physicist and cosmologist Subir Sarkar of the University of Oxford has noted, if we are indeed living in a void, this would affect our interpretation of cosmological data in fundamental ways. The KBC void is not simply an interesting feature of our cosmic neighborhood, it is a potential threat to the foundations of modern cosmology. The implications began unfolding almost immediately. If we live inside a region of space that is 20% less dense than the cosmic average, then every measurement we make of the universe's properties is potentially biased. When we look outward through the void and measure how fast distant galaxies are receding from us, we may not be seeing the universe's true expansion rate. We may be seeing a local distortion inflated by the gravitational effects of the void itself. This realization offered a tantalizing explanation for one of the deepest crises in modern physics. a crisis called the Hubble tension, which we will explore in depth later in our journey. But first, we need to understand what the void actually is, what fills it, what does not fill it, and why the physics of emptiness is far stranger than the word empty suggests. Take a slow breath. Let the night hold you. We are just getting started. Part 2. What fills the space between nothing? The word void suggests emptiness, absence, nothingness. But cosmic voids are not truly empty, and that is part of what makes them so strange. Between the few lonely galaxies scattered through these vast, underdense regions stretches space that contains dark matter, dark energy, and occasional wisps of hydrogen gas so diffuse that a cubic meter of void space holds fewer atoms than the most perfect vacuum chambers ever constructed on Earth. The density is so low that gravity, already the weakest of nature's 4 fundamental forces, barely registers. As the great physicist Richard Feynman once observed, gravity is the weakest force in nature, yet it is the one that shapes the universe. In voids, even that universe-shaping force retreats into near irrelevance. Without sufficient mass to pull things together, the process of structure formation essentially stops. No new galaxy clusters can coalesce. No rich superclusters can emerge. No intricate web of cosmic architecture can develop. The void stays a void, and it will remain one for the rest of cosmic time. This absence of gravitational dominance has profound consequences. To understand them, you need to appreciate the cosmic tug-of-war that governs the evolution of the universe. On one side stands gravity, the attractive force that pulls matter toward matter. It is the force that collapsed the first clouds of hydrogen into stars. It is the force that bound stars into galaxies, galaxies into clusters, and clusters into the vast web of filaments that spans the observable universe. Gravity builds structure. It concentrates matter. It resists the expansion of space. On the other side stands dark energy, the mysterious, repulsive pressure that permeates all of space and drives the accelerating expansion of the universe. Discovered in 1998 through observations of distant supernovae by the Supernova Cosmology Project and the High Z Supernova Search Team, a discovery that earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011. Dark energy accounts for approximately 68% of the universe's total energy content. According to NASA, dark energy is the name given to the unexplained force that is driving the accelerating expansion of the universe. In dense regions of the cosmos, where galaxies and galaxy clusters concentrate, gravity holds its own against dark energy. The mutual attraction of all that mass slows down the expansion of space locally, keeping structures bound together. Galaxy clusters do not fly apart despite the universe expanding around them, because the gravity within them is strong enough to resist. Inside voids, the story is entirely different. With so little mass to generate gravitational attraction, there is almost nothing to resist dark energy's push. Dark energy wins the tug-of-war decisively. The result is that voids expand faster than the rest of the universe. They grow like bubbles, their boundaries pushing outward against the surrounding filaments and walls of denser matter. And this process feeds on itself. The more a void expands, the more diluted its matter becomes. The less matter it contains, the weaker gravity's influence. The weaker gravity's influence, the more completely dark energy dominates. The more dark energy dominates, the faster the void expands. It is a runaway cycle, a cosmic feedback loop that ensures voids grow ever emptier over time. Scientists from the Sloan Digital Sky Survey and other major galaxy mapping projects have confirmed this through direct observation. They measured the velocities of galaxies near void edges and found them rushing away from the void centers faster than cosmic expansion alone can explain. As the astrophysicist Paul Sutter, who has studied void dynamics extensively, has written, "Voids are not just empty spaces. They are active, evolving structures that push matter away from their centers." The gravitational mechanism is counterintuitive until you think carefully about the geometry. Imagine standing in a shallow valley, surrounded by mountains on all sides. Gravity pulls you toward the mountains, which means it pulls you away from the valley center. Inside a cosmic void, the same principle applies. All the dense matter, the galaxies, the clusters, the filaments, lies outside the void, surrounding it in a shell of higher than average density. That exterior matter exerts a gravitational pull on everything inside the void, tugging it outward toward the walls. Our own galaxy participates in this process. The Milky Way is moving away from the nearby local void, a distinct but connected underdense region, at approximately 600,000 miles per hour. This motion is not driven by the expansion of space. It is a peculiar velocity, a gravitational response to the uneven distribution of matter around us. We are, quite literally, falling away from emptiness and toward the nearest concentration of mass. The interior of a void also becomes a strange place for light. Photons traveling through a void experience less gravitational influence than photons passing through denser regions. This affects observations in subtle but measurable ways. When astronomers study the cosmic microwave background, the faint afterglow of the Big Bang that fills the entire sky with radiation at a temperature of approximately 2.725 Kelvin, they notice that light passing through voids appears slightly cooler than light that has traveled through denser regions. This is called the integrated Sachs-Wolf effect, named after Rainer Sachs and Arthur Wolf, who predicted it in 1967. As a photon enters a void, it falls into a region of slightly lower gravitational potential, gaining a tiny amount of energy. As it exits the void, it climbs back out, losing energy. If the void were static, these effects would cancel perfectly. But because the void is expanding due to dark energy, the gravitational landscape changes during the photon's transit. The potential well becomes shallower while the photon is inside it, so the photon loses slightly more energy climbing out than it gained falling in. The net result is a tiny temperature decrease, a cold spot in the cosmic microwave background. ESA's Planck satellite, which mapped the cosmic microwave background with unprecedented precision from 2009 to 2013, confirmed that these cold spots align with known void locations. The correlation is statistically significant and matches theoretical predictions. As the Planck collaboration reported, the observed temperature decrements are consistent with the integrated Sachs-Wolf effect arising from large-scale structure. This is physics at its most elegant, the faint glow of the Big Bang, light that has been traveling through space for 13.8 billion years, carries within it the fingerprints of every void it has passed through on its way to our telescopes. The voids leave their mark on the oldest light in the universe. Take a breath here. Feel the quiet of this moment. You exist inside a region of space where gravity has lost its grip, where dark energy reigns, and where even ancient light is subtly altered by the emptiness surrounding you. This is not science fiction. This is your actual cosmic address. And the structure that contains this void, that frames it, that makes it possible, is far stranger than anyone imagined. Part 3. Who built the largest structure in nature? The universe is not a smooth, uniform soup of galaxies scattered evenly across space. It is organized into the most intricate architecture imaginable, a structure so vast that it took decades of observation and millions of galaxy measurements to reveal its true form. It is called the cosmic web, and it is the largest structure in the known universe. Imagine, if you can, a three-dimensional network of threads stretching across billions of light years. Where the threads intersect, matter concentrates into enormous nodes, galaxy clusters containing hundreds or thousands of galaxies bound together by gravity. These clusters are the densest structures in the cosmos, blazing with the combined light of trillions of stars and surrounded by superheated gas reaching temperatures of hundreds of millions of degrees, gas so hot it emits X-rays detectable by space telescopes like NASA's Chandra X-ray Observatory. Stretching between the nodes are the filaments, long chains of galaxy groups and smaller clusters that can extend for hundreds of millions of light years. These filaments form sheets and walls where galaxies gather in higher than average concentrations. The Sloan Great Wall, discovered in 2003 by J. Richard Gott and his colleagues using data from the Sloan Digital Sky Survey, is one such structure. A filament nearly 1.5 billion light-years long. It was, at the time of its discovery, the largest known structure in the universe. And between the filaments and walls lie the voids, the enormous, nearly empty bubbles that take up most of the volume of the cosmos while containing hardly any of its mass. The cosmic web was not always visible to us. For most of the history of astronomy, we saw the sky as a two-dimensional canvas. Galaxies appeared as points of light scattered across the celestial sphere, and while astronomers could see that some regions had more galaxies than others, the true three-dimensional arrangement remained hidden. Distance measurements were poor. Two galaxies that appeared side by side in the sky might actually be separated by billions of light years, one much farther away than the other. The revelation came in the 1970s and 1980s, when astronomers began measuring galaxy redshifts systematically on a large scale. Redshift, the stretching of light toward longer wavelengths caused by the expansion of space, provides a direct measure of distance. The more redshifted a galaxy's light, the farther away it is. By measuring redshifts for thousands and then hundreds of thousands of galaxies, astronomers could construct three-dimensional maps of the universe for the first time. The results were astonishing. As the astronomer Margaret Geller, who along with John Huchra created some of the first large-scale redshift maps in the late 1980s, described it. We expected to see a random scattering. Instead, we found a pattern of structures far larger than anyone had predicted. Their survey revealed galaxies arranged along thin walls and filaments with enormous empty regions between them. The universe had structure on scales that no one had anticipated. The first major void discovery came in 1981 when Robert Kirshner, Augustus Umler, Paul Schechter, and Stephen Scheckman identified the Bode's Void, a region roughly 330 million light-years across, containing very few galaxies. It was the first supervoid to be recognized, and it sparked intense interest in the distribution of galaxies on the largest scales. More surveys followed, each mapping deeper into space and revealing an increasingly intricate web. The 2-degree field galaxy redshift survey, completed in 2002, mapped over 220,000 galaxies. The Sloan Digital Sky Survey, which began observations in 2000 and continues in various phases to this day, has mapped the positions and distances of millions of galaxies across billions of light years. These surveys show the cosmic web in stunning three-dimensional detail. Filaments twist and branch like blood vessels in a living organism. Voids appear as dark, spherical bubbles, some 500 million light-years across. At the intersections of filaments sit enormous galaxy clusters, the bright nodes of the web. As the cosmologist John I. Nasto, one of the pioneers of large-scale structure research, has written, "The universe on the largest scales is neither uniform nor random. It is a complex web of filaments, walls, and voids, organized in a pattern that reflects the initial conditions of the Big Bang and the physics of gravitational collapse. But why? Why does the universe organize itself this way? The answer is one of the most beautiful stories in all of physics, and it reaches back to the very first moments of existence. In the first fraction of a second after the Big Bang, during a period called cosmic inflation, the universe expanded exponentially. In approximately 10 to the negative 35 seconds, a time interval so small it defies comprehension, the universe grew from a region smaller than an atom to a volume larger than the observable universe today. This extraordinary expansion was driven by a hypothetical field called the inflaton, and it smoothed out the universe to near-perfect uniformity. Near perfect, but not quite perfect. Quantum mechanics, the physics of the subatomic world, ensures that nothing can be perfectly uniform. Even empty space is subject to quantum fluctuations, tiny, random variations in energy that arise from the Heisenberg uncertainty principle. As the physicist Stephen Hawking wrote, "The universe does not allow you to have nothing. Even the vacuum has energy, and that energy fluctuates." During inflation, these quantum fluctuations were stretched from subatomic scales to cosmic scales. A fluctuation that began smaller than a proton could end up spanning millions of light years. These stretched fluctuations imprinted slight variations in the density of matter and energy across the infant universe. In some regions, density was a tiny bit higher than average. In others, a tiny bit lower. The variations were incredibly small, approximately 1 part in 100,000. But they were enough. After inflation ended, the universe continued expanding, but gravity began its slow, patient work. Regions that started slightly denser attracted more matter from their surroundings, becoming denser still. This was a positive feedback loop. The denser a region became, the more strongly it pulled matter toward itself. Over hundreds of millions of years, these overdense regions collapsed into the first stars, then galaxies, then clusters of galaxies, then the filaments and walls of the cosmic web. Meanwhile, regions that started slightly less dense experienced the opposite process. Matter drained away from them toward the denser regions, leaving them emptier. As matter departed, gravity weakened further, accelerating the drainage. These underdense regions grew into the voids. The process is called gravitational instability, and it is one of the most powerful organizing principles in nature. As the Nobel laureate James Peebles, who received the Nobel Prize in Physics in 2019 for his theoretical contributions to cosmology, has explained, the large-scale structure of the universe grew from tiny initial perturbations through the action of gravity over cosmic time. The web of filaments and voids we see today is the direct descendant of quantum fluctuations in the first moments after the Big Bang. The cosmic microwave background radiation provides a snapshot of these initial density variations when the universe was only 380,000 years old. At that epoch, the variations were still tiny, visible only as slight temperature differences of about 100 millionths of a degree across the sky. Warmer spots had slightly higher density. Cooler spots had slightly lower density. 3 generations of satellite missions have mapped these temperature variations with increasing precision. NASA's Cosmic Background Explorer, launched in 1989, made the first detection. NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, created the first high-resolution maps. ESA's Planck satellite, launched in 2009, produced the most detailed maps yet, revealing temperature fluctuations with an angular resolution of about 5 arc-minutes. Scientists can take these maps and use them as initial conditions for computer simulations, running the universe forward in time through 13.8 billion years of gravitational evolution. The simulations performed on some of the world's most powerful supercomputers reliably produce cosmic webs that closely resemble what we observe. The match between simulations and observations is one of the great triumphs of modern cosmology. It confirms that our understanding of how gravity shapes structure over cosmic time is fundamentally correct. And yet, the simulations rarely produce voids as large or as deep as the KBC void. They rarely produce structures as extreme as what we find ourselves sitting inside. This is where the beauty of the story begins to crack. The elegant picture of quantum fluctuations growing into cosmic structure works brilliantly in general. But in the specific case of our cosmic neighborhood, it fails to account for the scale and depth of the emptiness surrounding us. We will return to that tension. It will grow. It will become one of the central questions of our journey tonight. For now, sit with this. Every galaxy you have ever seen in a photograph, every cluster, every wall and filament of the cosmic web, every void between them, all of it traces back to quantum fluctuations smaller than an atom, stretched across the universe by inflation and amplified by gravity over billions of years. The largest structures in the cosmos are the direct descendants of the smallest fluctuations in nature. As the physicist Carl Sagan once said, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. Perhaps we are also a way for the universe to know its own architecture, to look back across billions of light years and billions of years and trace the threads of the cosmic web back to their quantum origins." Today, voids occupy roughly 90% of the total volume of space. The filaments and clusters, where galaxies crowd together in dazzling concentrations, make up the remaining 10%, but that 10% contains most of the mass. We live not in a cosmos filled with galaxies, but in a cosmos of emptiness, punctuated by occasional brilliant concentrations of matter. The KBC void is just one bubble in this vast foam, but it happens to be our bubble. And that, as we are about to discover, makes all the difference. Take a slow breath. Let the architecture of the universe settle into your mind. Filaments like threads of light, voids like bubbles of darkness, and you, here, inside one of them, listening to this in the quiet of the night. When we return, we will ask the next question. Where exactly do we sit inside this immense hollow? And what does our position mean for everything we think we know? Rest here for a moment. The journey continues. Part 4. Where exactly do we sit inside this emptiness? The Milky Way is not at the center of the KBC void, but it is close enough to matter. Measurements place our galaxy somewhere between 200 and 400 million light-years from the void's actual center. That might sound like an enormous distance, and compared to anything in human experience, it is. 400 million light-years is roughly 4,000 times the diameter of our entire galaxy. It is a distance so vast that light itself, traveling at 186,000 miles per second, requires 400 million years to cross it. If you had begun that journey when the first complex multicellular life was emerging on Earth, you would only now be arriving. But the void extends outward for approximately 1 billion light-years in every direction from its center. Our offset from the center, large as it is, represents a relatively small fraction of the void's total extent. We sit well within the underdense region, surrounded by the void's low-density environment in all directions. No matter which way we point our telescopes, we look through approximately 1 billion light-years of emptiness before reaching the denser walls beyond. This position is not merely a curiosity. It has consequences for every observation we make and every conclusion we draw about cosmology. If we were located outside the void entirely, in one of the dense filaments of the cosmic web, our measurements of the universe's expansion would look completely different. We would calculate a slower expansion rate. The mysterious discrepancy known as the Hubble tension would not exist. Our understanding of the cosmos, while perhaps still incomplete in other ways, would not be haunted by the specific crisis that currently divides the field. But we are not in a filament. We are in the void. And that accident of cosmic geography shapes everything. Our larger cosmic neighborhood adds layers of complexity to this story. The Milky Way belongs to the local group, a modest collection of about 80 galaxies gravitationally bound to one another. Our nearest large neighbor is Andromeda, a spiral galaxy roughly 2.5 million light-years away, visible to the naked eye on clear, dark nights as a faint smudge of light in the constellation that bears its name. The local group also includes the Triangulum Galaxy, the large and small Magellanic Clouds, and dozens of smaller dwarf galaxies, all orbiting one another in a gravitational dance that has persisted for billions of years. The local group itself sits within a far larger structure. In 2014, a team of astronomers, led by R. Brent Tully of the University of Hawaii, published a landmark paper in the journal Nature defining a vast cosmic structure they called Laniakea, from the Hawaiian words meaning immeasurable heaven. As Tully described it, Laniakea is a supercluster containing roughly 100,000 galaxies spread across 520 million light-years, all flowing together like water in a cosmic watershed, drawn toward a central gravitational attractor known as the Great Attractor. The Great Attractor is one of the most mysterious features of our cosmic neighborhood. Located in the direction of the Centaurus and Norma constellations, it represents a region of space with sufficient gravitational pull to influence the motion of galaxies across hundreds of millions of light-years. For decades, astronomers struggled to study it because it lies behind the plane of our own galaxy, obscured by the dense star fields and dust clouds of the Milky Way's disk. NASA's Chandra X-ray Observatory and other instruments have gradually revealed that the Great Attractor region contains a massive concentration of galaxy clusters, including the Norma cluster, which lies close to the center of the gravitational anomaly. The Milky Way sits on the outskirts of Laniakea, part of this vast drainage basin where galaxies flow toward the Great Attractor. The entire supercluster moves coherently, bound together by gravitational flows that override cosmic expansion on these scales. Think of Laniakea as a watershed on Earth, where all rivers and streams flow downhill toward the same ocean. Except the terrain is not made of rock and soil. It is the curvature of space-time itself, shaped by the distribution of matter and energy across hundreds of millions of light-years. Now here's the paradox that should keep you awake tonight, though I hope it does not. Laniakea, despite containing 100,000 galaxies, resides entirely within the KBC void. Think about that for a moment. A structure containing 100,000 galaxies, one of the largest bound structures in the observable universe, still counts as part of an underdense region. The void is so vast, so encompassing, that it can swallow entire superclusters and still have room to spare. Laniakea forms part of the sparse population of matter scattered through the void, one of the rare concentrations in an otherwise barren expanse. It is like a small town in the middle of a continental desert. The town exists. People live there, but the desert defines the landscape. The resolution of this apparent paradox lies in how density is measured. The KBC void is underdense compared to the cosmic average when measured over very large scales, over volumes of billions of cubic light-years. But it is not uniformly empty. Within it, there are filaments, which contain clusters, which contain groups, which contain galaxies, which contain stars and planets, and, on at least one of those planets, a species that has learned to measure the density of the cosmos. Structure exists at every scale, The void is defined by the absence of the richest superclusters and the most massive galaxy clusters at its center, not by the complete absence of matter. As the cosmologist R. Brent Tully has noted, structure in the universe is hierarchical. What counts as a void depends on the scale at which you measure. The KBC void describes the average properties over billions of light years. Laniakea describes the local properties over hundreds of millions of light years. Both are real. Both matter. They simply describe different levels of the cosmic hierarchy. The local group is also influenced by another nearby void, distinct from but connected to the larger KBC void. It is called simply the local void. Extending about 200 million light years, the local void sits adjacent to our position in space. Our galaxy is rushing away from it at approximately 600,000 miles per hour, driven by the gravitational pull from denser regions beyond. This motion is separate from the overall cosmic expansion. It is what astronomers call a peculiar velocity, a motion arising from local gravitational effects rather than from the stretching of space itself. These peculiar velocities complicate efforts to measure the true expansion rate of the universe. They add extra motion on top of the expansion signal, motion that must be carefully identified and subtracted before the underlying expansion can be determined. But inside a supervoid, those corrections are amplified and harder to separate cleanly. The void creates large-scale velocity fields that extend over hundreds of millions of light years, affecting everything within it. When scientists measure the motions of galaxies out to distances of 250 million light years, they find something troubling. They find bulk flows, coherent patterns of galaxy motion that exceed the predictions of standard cosmology. Entire regions of space are moving faster than they should be, flowing in lockstep away from the underdense region and toward the denser structures beyond. The Cosmic Flows Project, led by Tully and his collaborators, has mapped these bulk flows in unprecedented detail using data from thousands of galaxies. The flows are real, significant, and difficult to explain without invoking a large-scale underdensity like the KBC void. Galaxies inside the void are not just sitting passively in empty space, expanding along with the universe. They are actively responding to the gravitational landscape, accelerating outward from the underdensity toward denser structures beyond the void's edge. Our local patch of the universe is more dynamic, more unusual, and more structured than the calm, uniform cosmos that standard models assume. Our position inside the void also affects what we can see. Light from distant galaxies travels through the void on its way to our telescopes, experiencing less gravitational interaction than light traveling through denser regions. When we look outward from inside the void, we see the shell of denser material surrounding us in all directions. That shell appears as a concentration of galaxy clusters and filaments at a specific distance range. Beyond the shell, the universe returns to more typical density. This creates an observational bias that is extraordinarily difficult to correct for. We are not sampling a random location in the universe. We are sampling from inside one of its most extreme features. Take a slow breath. Feel the weight of that. Everything you have ever learned about the cosmos, every number, every measurement, every grand conclusion about the age and fate of the universe was made from inside this hole, and the hole may be distorting what we see. Part 5. Can a hole in space lie to us about the universe? Every measurement you have ever heard about the universe's expansion rate might be wrong. Not because scientists made mistakes, not because the instruments are flawed, not because anyone cut corners or overlooked obvious errors. The measurements might be wrong because we are measuring from inside a cosmic hole that systematically distorts the signal. And the distortion is large enough to explain one of the most stubborn crises in all of modern physics. The crisis is called the Hubble tension. and it has been growing for over a decade. It is named after Edwin Hubble, the astronomer who first demonstrated in 1929 that the universe is expanding, that distant galaxies are moving away from us, and that the speed of their recession is proportional to their distance. The constant of proportionality, the number that encodes how fast the expansion is occurring, is called the Hubble constant, designated h0. Measuring the Hubble constant is one of the most important tasks in cosmology. It determines the expansion rate of the universe, which in turn determines the age of the universe, the density of matter and energy, the properties of dark energy, and the ultimate fate of the cosmos. Get the Hubble constant right, and much of cosmology falls into place. Get it wrong, and the entire framework trembles. There are two primary ways to measure it. Each is independent, each is extraordinarily precise, and they disagree. The first method looks backward in time to the very beginning. The cosmic microwave background, the faint afterglow of the Big Bang, encodes information about the universe when it was only 380,000 years old. By analyzing the pattern of temperature fluctuations in this ancient light, scientists can determine the density, composition, and expansion rate of the early universe with remarkable precision. ESA's Planck satellite, which mapped the cosmic microwave background from 2009 to 2013 with unprecedented accuracy, determined the Hubble constant to be approximately 67.4 kilometers per second per megaparsec. That means for every megaparsec of distance, roughly 3.26 million light years, the expansion of space adds 67.4 kilometers per second to the recession velocity of a distant object. The second method looks at the nearby universe, using objects whose brightness is well understood. Type 1. A supernovae, the thermonuclear explosions of white dwarf stars, serve as standardizable candles because their peak brightness can be calibrated with high precision. Cepheid variable stars, whose pulsation periods correlate with their intrinsic brightness, provide another rung on what astronomers call the cosmic distance ladder. By measuring the apparent brightness of these objects and comparing it to their known true brightness, astronomers calculate their distance. Combining distance with redshift gives the expansion rate directly. The local measurement, refined over years by teams led by Nobel laureate Adam Rees of Johns Hopkins University and the Space Telescope Science Institute, consistently produces a higher number, approximately 73.0 kilometers per second per megaparsec. The difference between 67.4 and 73.0 is about 9%. That sounds small. It is not. Both measurements have error bars that are tiny, so small that they do not overlap. The discrepancy has reached what physicists call 5 sigma significance, meaning there is less than a 1 in a million chance that it is a statistical fluke. As Rees himself has stated, the tension between local and early universe measurements of the Hubble constant has now reached a level that cannot be dismissed as a fluke. Either we are missing something in our understanding of the early universe, or we are missing something about the local universe. The KBC void offers a compelling explanation for the discrepancy. When we measure the expansion rate using nearby supernova, we are measuring within the void. The void's low density means there is less gravity pulling back on the expansion in our region. Galaxies within the void are not only being carried outward by cosmic expansion, but are also being pulled outward by the gravitational attraction of the denser matter surrounding the void. This adds extra velocity to their recession, inflating the apparent expansion rate. We are not measuring the universe's true expansion rate. We are measuring the expansion rate plus the void's peculiar velocity field. The two signals are entangled, and separating them requires knowing the void's properties with great precision. When scientists model the gravitational effects of a void matching the KBC's size and depth, they find that it could boost the apparent expansion rate by approximately the amount needed to explain the tension. The match is not perfect, and not all researchers agree on the magnitude of the effect, but the direction is right and the order of magnitude is right. The void hypothesis is, at minimum, a serious contender. As the cosmologist Hélène Courtois of the University of Lyon, who co-discovered the Laniakea supercluster, has observed, the local universe is not a fair sample of the cosmos. We must be very careful about generalizing from local measurements. But if the void explains our local measurements, those measurements are systematically biased by our location. And that leads to a deeply uncomfortable conclusion. The cosmological principle, one of the foundational assumptions of modern physics, states that the universe is homogeneous and isotropic on sufficiently large scales. No location is special. No direction is preferred. The universe should look roughly the same from any vantage point once you average over large enough volumes. This principle is what allows cosmologists to model the entire universe using relatively simple equations. Without it, the mathematics becomes vastly more complicated. Finding ourselves inside a supervoid that significantly affects our measurements seems to contradict this principle. It suggests we are in an unusual location. It implies that Earth, despite centuries of progressive decentering, from Copernicus to Hubble, might occupy a special cosmic position after all. Not the center of the universe, but a position sufficiently atypical to bias our understanding of cosmic properties. As Albert Einstein once wrote, "The eternal mystery of the world is its comprehensibility." But what if the world is less comprehensible than we thought, not because it is inherently mysterious, but because we are looking at it from the wrong place? The debate continues. Not all cosmologists accept the void explanation. Some argue that even a void as large as the KBC cannot produce a big enough effect to fully account for the tension. Others point out that supervoids this large should be exceedingly rare, and finding ourselves in one, just when we have developed the precision to measure the Hubble constant, seems suspicious. Still others propose that the tension arises from new physics in the early universe, perhaps an extra burst of expansion, or a change in the properties of dark energy, or a modification to general relativity that alters the predictions of the standard model. The controversy remains unresolved. The Hubble tension continues to be called a crisis precisely because no explanation has achieved consensus. It is not just a number that is off. It is a signal that our understanding of the cosmos might be incomplete in ways we have not yet imagined. Take a slow breath. Let the uncertainty sit with you for a moment. It is all right not to have the answer. Even the universe, it seems, does not have the answer yet. Part 6. What if gravity works in reverse? Gravity inside a void does something that sounds impossible. It pushes outward. This is not because gravity itself reverses. The force of gravity always attracts mass toward mass. That is its nature, written into the equations of general relativity and confirmed by every observation from falling apples to merging black holes. But the geometry of a void creates a situation where the net gravitational effect on objects inside it is directed outward, away from the center, and toward the surrounding walls of denser matter. The mechanism is simple once you understand the distribution of mass. Inside a void, matter is sparse. Outside the void, in the filaments, walls, and clusters of the cosmic web, matter is dense. That dense exterior matter exerts a gravitational pull on everything inside the void, tugging galaxies toward the walls and away from the void center. The result is a systematic outflow. Galaxies inside voids are not just expanding along with the universe, they are accelerating outward, falling toward the nearest concentrations of mass like water flowing downhill toward a river valley. The effect is measurable and significant. Astronomers track these motions using a combination of redshift measurements and independent distance estimates. Redshift alone mixes two signals: the expansion of space and the peculiar motion of each galaxy due to local gravity. To isolate the peculiar velocity, you need a distance measurement that does not depend on redshift. Techniques like the Tully-Fisher relation, which relates a spiral galaxy's rotation speed to its intrinsic brightness, and the fundamental plane relation for elliptical galaxies, provide these independent distances. By comparing the redshift-based velocity to the distance-based velocity, astronomers can extract the peculiar velocity for each galaxy. When they map these peculiar velocities around known voids, the pattern is unmistakable. Galaxies near void centers are moving outward faster than cosmic expansion alone predicts. The effect is strongest near the center and weakens toward the edges, where matter density increases. For the KBC void specifically, the outflow adds hundreds of kilometers per second to galaxy velocities within the void. The Milky Way participates in this pattern. Our galaxy is moving at approximately 627 kilometers per second relative to the cosmic microwave background rest frame, a velocity that results from the combined gravitational influences of the local void, the Virgo cluster, the Great Attractor, and the Shapley supercluster. This total peculiar velocity was measured by observing the dipole anisotropy in the cosmic microwave background, a slight temperature difference between the direction we are moving toward and the direction we are moving away from, first detected by NASA's COBE satellite in the early 1990s. As the physicist and Nobel laureate George Smoot, who led the COBE dipole measurement, stated, "The dipole pattern in the cosmic microwave background tells us that the Milky Way is not at rest with respect to the radiation from the Big Bang. We are moving through the universe at a considerable velocity." That velocity, 627 kilometers per second, translates to approximately 1.4 million miles per hour. At that speed, the Milky Way travels about 167 miles every second. In a single year, we move roughly 5.2 billion miles through space relative to the cosmic microwave background frame. But even at this breakneck pace, the void is so vast that our motion barely makes a dent. It would take hundreds of millions of years to cross from one side of the KBC void to the other, and the void continues expanding faster than we can traverse it. We are inside it now, and we will remain inside it for the foreseeable cosmic future. This high velocity is itself evidence for the void. In a universe that is truly homogeneous on large scales, peculiar velocities should be modest. If matter is distributed evenly, gravitational pulls from different directions should roughly cancel out, leaving galaxies with small residual motions of perhaps 100 to 200 kilometers per second. The fact that our peculiar velocity is more than 3 times that amount indicates strong gravitational gradients in our vicinity, exactly what you would expect from being near a large, underdense region. The outflow from the void also affects cosmic expansion measurements in a way that compounds the Hubble tension. When we observe distant galaxies and measure their redshift, we see a combination of the expansion of space and the peculiar velocity of galaxies due to the void's gravitational influence. Normally, peculiar velocities average out when you look at large enough volumes. For every galaxy moving toward you due to local gravity, another is moving away, and the average is 0. But inside a void, the peculiar velocities do not average out. They all point in the same direction, outward. This creates a systematic bias that inflates the apparent expansion rate when measured from within the void. The problem compounds at different distance scales. Close to the void center, the outflow is rapid. Farther from the center, but still within the void, it is slower. Beyond the void's edge, peculiar velocities might even reverse as matter falls back toward the denser filaments. This creates a complicated velocity profile that varies with distance. When astronomers measure the Hubble constant, Using supernovae at different distances, they are sampling this varying velocity field. If most of their supernovae lie within the void, which they typically do, the measurement gets boosted by the outflow. This predicts something specific and testable. The apparent Hubble constant should decrease with distance. Nearby measurements should yield the highest values. As you look farther out, approaching the void's edge, the value should decline toward the cosmic average. Recent observations are beginning to confirm exactly this trend. The modeling of these effects requires careful calculation. Scientists must estimate the void's size, depth, and density profile, then compute the gravitational potential it creates. That potential determines how fast material flows outward at each radius. The calculations show that a void roughly 1 billion light-years in radius, with a 20% density deficit, can produce velocity anomalies matching observations. The agreement between predictions and data is strong enough that many researchers find the void explanation compelling. But the standard model struggles to explain how such a large void formed in the first place. And that struggle leads us to one of the deepest questions in all of cosmology: whether the fundamental rules governing the universe are what we think they are. Take a breath here, a slow one. Let the night hold you. We have traveled through the discovery of the void, explored its strange physics, and confronted the crisis it creates for our understanding of cosmic expansion. When we return, we will ask whether the void violates the most sacred principle in physics, and whether the quantum fluctuations that gave birth to the cosmos might be stranger than anyone suspected. Rest here for a moment. The universe will wait. Part 7. Does our location violate the most sacred principle in physics? The cosmological principle is one of the oldest and most deeply held assumptions in the history of science. In its modern form, it states that the universe is homogeneous and isotropic on sufficiently large scales. Homogeneous means the same everywhere. No location is special, preferred, or fundamentally different from any other, once you average over large enough volumes. Isotropic means the same in all directions. The universe should look statistically identical no matter which way you turn your gaze. These are not minor assumptions. They are the foundation upon which nearly all of modern cosmology is built. The Friedmann equations, which describe how the universe expands, assume homogeneity and isotropy. The standard model of cosmology, lambda CDM, assumes them. The interpretation of the cosmic microwave background, the calculation of the universe's age, the determination of dark energy's properties, all of these rest on the cosmological principle. The principle is also the culmination of a centuries-long philosophical journey. Before Copernicus, Earth occupied the center of the cosmos. The sun, the moon, the planets, and the stars all revolved around us. Copernicus displaced Earth from the center, placing the sun there instead. Later observations showed that the sun was not at the center of the galaxy. The galaxy was not at the center of the universe, and eventually, the cosmological principle declared that there is no center at all, because every location is equivalent, as the physicist and cosmologist Hermann Bondi expressed it in the 1950s. The cosmological principle is the assertion that the universe presents the same aspect from every point. It is the ultimate expression of cosmic humility. We are not special. Our location is not special. The universe does not care where we are. The KBC void threatens to shatter this principle. If the void is 2 billion light-years across with a 20% density deficit, that is a massive inhomogeneity. The void is not small compared to the observable universe. It represents a significant fraction of the volume within several billion light-years of Earth. Finding ourselves near the center of this abnormal structure contradicts the idea that our location is unremarkable. The statistical rarity makes the tension worse. In a universe governed by standard cosmology, a void as large and deep as the KBC void should be exceedingly rare. Some calculations place it at a 10 sigma deviation from the expected density distribution. In a typical random realization of the universe's structure, simulated from the initial conditions of the cosmic microwave background and evolved forward through 13.8 billion years, you might not find a single example of such a void anywhere in the observable cosmos. The probability of our galaxy happening to reside inside one, given how rare they should be, strains credulity. As the physicist David Wiltshire of the University of Canterbury in New Zealand has argued, if the KBC void is real and as significant as measurements suggest, we must seriously consider whether the assumption of large-scale homogeneity is correct. The foundation of standard cosmology may need to be re-examined. Defenders of the cosmological principle offer several counter-arguments. The most common is that homogeneity applies only at scales of several hundred megaparsecs or larger. The KBC void is approximately 600 megaparsecs across, which is right at the boundary of where homogeneity is supposed to kick in. Perhaps the universe is simply less smooth at those transitional scales than previously assumed. If the threshold for homogeneity is pushed to larger scales, the void becomes less of a violation. Another defense invokes observational uncertainty. Different teams using different data sets and techniques have measured somewhat different properties for the void. Some find a 20% density deficit. Others find closer to 10 or 15%. If the true deficit is on the lower end, the statistical rarity becomes less severe, though it remains a challenge for standard models. A third defense appeals to the anthropic principle, the idea that observers can only exist in certain types of environments. Perhaps intelligent life requires galaxies to form in regions that are neither too dense nor too sparse. If most observers naturally find themselves in mildly underdense regions, then our location in a void is less surprising. But this argument has limits. A 20% deficit is more than mild. It pushes beyond what the anthropic principle can comfortably explain away. The debate remains unresolved. Some researchers believe the void is real and significant, requiring either modifications to cosmology or the acceptance that Earth occupies a genuinely unusual position. Others believe the void is an observational artifact, or not as extreme as initially reported. Still others propose that the cosmological principle holds on even larger scales and that the apparent violation is a feature of the transitional regime between structured and homogeneous scales. Future observations will help settle this. Surveys that map the universe to greater distances and depths, like the Dark Energy Spectroscopic Instrument, or DESI, which began operations in 2021, and the Vericy-Rubin Observatory's Legacy Survey of Space and Time, scheduled to begin in the mid-2020s, will reveal whether large voids are as rare as standard models predict, or whether they are more common than expected. If big voids turn out to be frequent, the cosmological principle survives, but the standard model needs revision. If they are truly rare, we need to explain why we happen to live in one. Either way, the question is profound. Is the universe truly the same everywhere? Or have we been assuming a symmetry that does not exist? Take a slow breath. Let that question linger. It does not need an answer tonight. Sometimes the most important questions are the ones you carry with you, turning them over slowly in the dark. Part 8. Did quantum chance decide we would live in a desert? The voids we observe today, including the KBC void that surrounds us, began as infinitesimal quantum ripples in the first moments after the Big Bang. Their origin is one of the most remarkable stories in all of science, connecting the smallest phenomena in nature to the largest structures in the cosmos. During the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion called inflation. In approximately 10 to the negative 35 seconds, a time interval almost impossibly brief, the universe expanded by a factor of at least 10 to the 26th power. A region smaller than a proton was stretched to a size larger than the observable universe today. This expansion was not just fast, it was transformative. It took the quantum fluctuations of the vacuum, the tiny, random variations in energy density that quantum mechanics requires to exist in even the emptiest space, and stretched them across cosmic scales. A fluctuation that began at the Planck scale, roughly 10 to the negative 35 meters, could end up spanning millions or even billions of light years. As the physicist Alan Guth of MIT, who first proposed the theory of cosmic inflation in 1980, has described it. Inflation is the mechanism by which the quantum fluctuations of the very early universe were stretched to produce the large-scale structure we observe today. The galaxies and voids of the cosmic web are, in a very real sense, quantum mechanics writ large. These stretched fluctuations imprinted slight variations in the density of matter and energy across the infant universe. In some regions, density was a tiny bit higher than average. In others, a tiny bit lower. The variations were incredibly small, approximately 1 part in 100,000. But as we have seen, gravity amplifies even the smallest advantages. After inflation ended and the universe continued its more gradual expansion, the process of gravitational instability began. Regions that started slightly overdense attracted more matter from their surroundings, becoming denser still. Regions that started slightly underdense lost matter to their neighbors, becoming emptier. Over hundreds of millions of years, this process turned barely perceptible density variations into the dramatic cosmic web of filaments, clusters, and voids. The cosmic microwave background provides a snapshot of these variations when the universe was only 380,000 years old. At that epoch, the density differences had grown slightly but were still tiny, visible only as temperature fluctuations of about 100 millionths of a degree. ESA's Planck satellite mapped these fluctuations with exquisite precision, revealing a pattern of hot and cold spots at various angular scales that encodes the initial conditions for all subsequent structure formation. Scientists use these maps as starting points for N-body simulations, massive computational experiments that track the gravitational evolution of billions of particles over 13.8 billion years of simulated cosmic history. The Millennium simulation, run in 2005 by the Virgo Consortium, using the supercomputers at the Max Planck Society's computing center in Garching, Germany, was one of the landmark efforts, tracking over 10 billion particles and producing a simulated cosmic web that closely matched observations. More recent simulations, like Illustrious TNG and the Eagle project, have added the physics of gas, star formation, and black hole feedback, producing even more realistic representations of the cosmos. These simulations reliably produce cosmic webs that resemble observations. Filaments, clusters, walls, and voids emerge naturally from the gravitational evolution of the initial density fluctuations. The statistical properties of the simulated webs, the distribution of void sizes, the clustering of galaxies, the power spectrum of density fluctuations, match observed properties with impressive accuracy. But the simulations have a problem. They rarely produce voids as large or as deep as the KBC void. The initial quantum fluctuations were random, governed by the statistics of quantum mechanics. Every region of the early universe had some probability of ending up as a void or a filament or a cluster. But probability distributions matter. Small voids, arising from common, modest underdensities, should be frequent. Large voids, requiring rare, extreme underdensities, should be correspondingly rare. The KBC void, with its 2 billion light-year extent and 20% density deficit, falls into the extremely rare category. One possibility is that the initial quantum fluctuations were not perfectly described by the simple statistical models used in standard inflation. Perhaps inflation produced more power on large scales than the simplest models predict. This could happen if the inflaton field, the hypothetical field that drove inflation, had a potential energy surface with features that enhanced large-scale fluctuations. Such models exist, but require additional assumptions beyond the minimal inflationary scenario. Another possibility is that the growth of structure after inflation was more efficient than standard models account for. If gravity is effectively stronger on large scales than general relativity predicts, or if dark matter has properties that enhance clustering, voids would grow deeper and larger than expected. We will explore this possibility in more detail when we discuss modified gravity. A third option is simply that the universe has more statistical variance than cosmologists expected. Random processes sometimes produce extreme outcomes. Perhaps the KBC void is the cosmic equivalent of a 1,000-year flood, rare but not impossible, and we happen to be living through one. Regardless of which explanation is correct, the quantum origin of the void remains profound. The cosmic desert we inhabit traces back to subatomic processes that occurred before atoms existed, before stars existed, before the universe was old enough to have any structure at all. Randomness at the smallest conceivable scales propagated upward through gravity and time to create structure at the largest scales. The cosmic web, with its filaments spanning billions of light years, is the direct descendant of quantum uncertainty at the Planck scale. As the physicist John Archibald Wheeler once wrote, "The universe is built on quantum randomness, and from that randomness emerges all the order, all the structure, all the beauty we observe." Our location within this structure is the result of chance. There is no reason we had to end up in a void rather than in a filament. The initial conditions in our region of the universe happened to be slightly underdense by 1 part in 100,000 or so, and gravity did the rest over 14 billion years. That accident of quantum chance, that tiny deficit of density in a patch of space that was smaller than an atom when it formed, determined what we observe when we look out at the cosmos today. Take a slow breath. You are the product of quantum randomness, amplified by gravity, stretched by inflation, and organized by time into the most complex structure the universe has ever produced. And you are listening to this here tonight, inside a void that was born from a quantum fluctuation before the first atom ever formed. Part 9. How empty can the universe really be? When you picture the universe, you probably imagine a sky full of stars and galaxies, a cosmos brimming with light and activity. Photographs from the Hubble Space Telescope and the James Webb Space Telescope reinforce this image, showing fields dense with galaxies stretching to the edge of the observable universe. But the reality is the opposite. The universe is overwhelmingly empty. Voids occupy roughly 90% of the total volume of space. The galaxies and galaxy clusters that fill our photographs and textbooks crowd into the remaining 10%, packed into the filaments, walls, and nodes of the cosmic web. That 10% contains most of the mass, but it occupies only a small fraction of the volume. If you could somehow travel through a void, you would fly for tens of millions of years at the speed of light without encountering a single galaxy. The isolation would be nearly absolute. Occasionally, you might pass a lonely dwarf galaxy drifting through the darkness, a small, faint collection of a few billion stars separated from its nearest neighbor by distances so vast that the light from that neighbor would take millions of years to arrive. These void galaxies evolve slowly, rarely interacting with anything. They are the galactic equivalent of hermits, living out their existence in profound solitude. As the astrophysicist Paul Sutter has described it, voids are not just holes in the cosmic web, they are the dominant feature. If you were to pick a random point in the universe, the overwhelming probability is that you would find yourself in a void, surrounded by nothing, with the nearest galaxy millions of light years away. This lopsided distribution creates a universe with two faces. In the dense filaments, galaxies interact, collide, and merge frequently. Star formation is vigorous. Supermassive black holes grow by accreting matter stirred up by galaxy mergers. Clusters of galaxies form and evolve rapidly, surrounded by superheated gas that emits X-rays detectable by telescopes like NASA's Chandra Observatory. The filaments are busy, dynamic, violent places where cosmic evolution proceeds at a rapid pace. In the voids, everything is quiet. The few galaxies present tend to be smaller, fainter, and less evolved than their counterparts in dense regions. Many are dwarf galaxies, barely massive enough to hold onto their gas against the outward pressure of stellar winds and supernovae. Star formation is sluggish. Many void galaxies contain large reservoirs of neutral hydrogen gas that have not yet condensed into stars, fuel that remains unburned because there are no nearby interactions to trigger its collapse. Void galaxies also tend to be morphologically different from cluster galaxies. Most are late-type spirals or irregular galaxies rather than the massive elliptical galaxies that dominate dense clusters. Ellipticals form primarily through galaxy mergers, which are rare in voids. Without mergers, galaxies maintain their disk structures and spiral arms, evolving slowly and peacefully over billions of years. Some void galaxies show remarkably undisturbed morphologies, smooth disk profiles, and regular rotation patterns that have never been battered by interactions or gravitational tides from neighbors. Even in voids, dark matter is present. Dark matter makes up approximately 85% of all matter in the universe, but does not interact with light, making it invisible to telescopes and detectable only through its gravitational effects. According to measurements from ESA's Planck satellite and other sources, the total matter density of the universe, including both ordinary and dark matter, is approximately 31% of the critical density. In voids, the matter density drops to roughly 15 to 20% of the cosmic average. That might sound like a lot, but spread over volumes spanning hundreds of millions of light years, the amount of dark matter per cubic light year is extraordinarily tiny. Dark energy, however, is uniformly distributed. It does not clump. It does not flow. It simply exists everywhere, at a constant density, filling every cubic centimeter of space with the same repulsive pressure. In dense regions, dark energy is overshadowed by the gravitational effects of concentrated matter. In voids, where matter is sparse, dark energy becomes the dominant component. This dominance has consequences for the future that we will explore later. For now, what matters is the present reality. 90% of the universe is void. Most of space is empty. And we, despite living in a galaxy that is itself part of a supercluster containing 100,000 galaxies, still find ourselves inside one of these vast empty regions. The KBC void is not the emptiest place in the universe. It is not the largest void ever discovered. That distinction may belong to the Eridanus supervoid, roughly 1.8 billion light-years across, discovered through its impact on the cosmic microwave background. But the KBC void is the void that matters most to us, because it is ours. We live inside it. We measure the universe from within it, and its emptiness shapes everything we see. Take a breath. Let the scale of that emptiness settle into you. 90% of the cosmos is void, and yet here you are, a concentration of atoms so improbable, so intricate, so utterly unlikely, that the universe had to work for 14 billion years to produce you. You exist on the edge between fullness and emptiness, between structure and void, between meaning and silence. Part 10. What if the void is impossible? The KBC void defies probability in a way that makes cosmologists deeply uncomfortable. We have touched on this tension already, but it deserves its own examination because the statistical improbability of the void is not a minor footnote. It is a flashing warning light that something may be fundamentally wrong with our understanding of how the universe works. Standard cosmology predicts that structures form through the gravitational amplification of initial density fluctuations. The larger and deeper a structure, the rarer it should be. This follows directly from the statistics of the initial fluctuations, which are well described by a Gaussian distribution, a bell curve. Most fluctuations are small, producing common, modest structures. Large fluctuations are rare, producing uncommon, extreme structures. Very large fluctuations are very rare, producing structures that should almost never appear. The KBC void, with its 2 billion light-year extent and 20% density deficit, falls into the category of structures that should almost never appear. When researchers run ensembles of simulated universes, generating hundreds or thousands of independent realizations of cosmic structure formation from randomized initial conditions, they search for voids matching the KBC void's properties. The yield is vanishingly small. Some studies find no matches at all in their entire ensemble. Others find a handful, always representing extreme statistical outliers. One analysis, published in the monthly notices of the Royal Astronomical Society, calculated that the void represents a density contrast of approximately negative 0.2 on a scale of roughly 300 megaparsecs. Under the Gaussian statistics of the Standard Model, this corresponds to a fluctuation of approximately 3 to 4 sigma for the most conservative estimates, and potentially as high as 10 sigma for less conservative analyses. As the authors noted, even at the lower end of these estimates, the probability of finding such a structure in the observable universe is uncomfortably small. This statistical tension creates a trilemma. 3 possible explanations, each of which requires abandoning or modifying something important. The first possibility is that the observations are wrong. Perhaps the void is not as large or as deep as measurements suggest. Different research groups using different data sets have produced somewhat different results. Some find a 20% density deficit. Others find closer to 10 or 15%. If the true deficit is on the lower end, the statistical rarity becomes less severe. Future surveys, particularly the Euclid Space Telescope launched by ESA in 2023 and the Vera C. Rubin Observatory's Legacy Survey, will provide much more precise measurements of the void's properties. Within a decade, we should know its true extent and depth to within a few percent. The second possibility is that the Standard Model's predictions for structure formation are wrong. Perhaps the initial fluctuations from inflation had more power on large scales than minimal models predict. Perhaps dark matter has properties that enhance the growth of large-scale structure. Perhaps there are additional physical processes in the early universe that amplified density contrasts beyond what the Standard Model accounts for. Any of these modifications could make large voids more probable and reduce the statistical tension. But each requires altering foundational aspects of cosmology that have been successful in other contexts. The third possibility is that we are simply extraordinarily lucky. Random processes produce extreme outcomes on occasion. The universe is vast enough that rare structures can appear somewhere within it, and we happen to inhabit one of them. This explanation requires no modification to physics, but it requires accepting that our location is genuinely unusual, which sits uneasily with the cosmological principle and the philosophical tradition of cosmic humility. As the statistician and cosmologist Andrew Jaffe of Imperial College London has cautioned, we must be careful about declaring structures impossible. The universe is large, and rare things happen. But when the rarity exceeds what our models predict, we should take that as a signal to examine the models more carefully. The KBC void has become a focal point for debates about the standard cosmological model precisely because it sits at the intersection of observation and theory, challenging our most basic assumptions about how the universe formed its structure. Critics of lambda CDM point to the void as evidence that the model fails on large scales. They argue that the void is not the only anomalously large structure. The Shapley supercluster, the Sloan Great Wall, the Eridanus supervoid, and other enormous features all suggest that structure formation is more vigorous than lambda CDM predicts. Defenders of the standard model counter that rare events sometimes happen, and that abandoning a framework that works brilliantly in so many other contexts based on a handful of extreme structures would be premature. They also note that the precise statistical significance of the void depends on assumptions about how to measure void properties and how to define the comparison sample, which introduces uncertainties that could reduce the apparent tension. The debate is healthy and productive. It is exactly the kind of confrontation between theory and observation that drives science forward, but it remains unresolved, and the void remains a cosmic puzzle that refuses to fit neatly into our current understanding. As the physicist Richard Feynman once said, "It does not matter how beautiful your theory is. It does not matter how smart you are. If it does not agree with experiment, it is wrong." The KBC void is the experiment. The question is whether it agrees with our theory, and right now, the answer is not entirely clear. Take a slow breath. Let the uncertainty hold you. Science is not a destination. It is a process of asking questions that lead to better questions. Tonight, we are in the middle of some of the best questions physics has ever asked. When we return, we will explore what the void teaches us about dark energy, whether Einstein's theory of gravity needs revision, and what happens when you are trapped inside a bubble of false measurements, unable to see the universe as it truly is. Rest for a moment. The cosmos will be here when you return. Part 11. Can emptiness teach us about the universe's deepest mystery? Cosmic voids are, paradoxically, the best places in the universe to study the force that is tearing the universe apart. Dark energy, the mysterious repulsive pressure that drives the accelerating expansion of the cosmos, remains one of the most profound unsolved problems in all of physics. Discovered in 1998, it accounts for approximately 68% of the universe's total energy content. It is everywhere. It fills every cubic centimeter of space with the same constant density, pushing the fabric of the universe outward, stretching the distances between galaxy clusters, thinning the filaments, and expanding the voids. According to NASA, dark energy is the name given to the unexplained force that is driving the accelerating expansion of the universe. Its nature is a complete mystery. The nature of dark energy is the question. Is it a cosmological constant, an unchanging energy density woven into the fabric of space-time itself, as Einstein first proposed in 1917, and then famously retracted as his greatest blunder? Or is it something dynamic, a field that varies in strength over time and space, evolving as the universe ages? Distinguishing between these possibilities is one of the central goals of modern cosmology, and voids, it turns out, are the ideal laboratories for the task. The reason is simple. In dense regions of the cosmic web, where galaxy clusters concentrate and gravity is strong, the effects of dark energy are entangled with the effects of gravity. Gravity pulls matter together, resisting expansion. Dark energy pushes space apart, driving expansion. Separating these competing influences requires careful modeling and introduces significant uncertainties. The gravitational field of a massive galaxy cluster can distort measurements, complicating any attempt to isolate dark energy's contribution. In voids, these complications largely disappear. Matter is sparse, gravity is negligible. Dark energy dominates the dynamics almost entirely. Galaxies within voids move primarily in response to cosmic expansion and dark energy, with minimal gravitational contamination from nearby structures. This makes voids the cleanest environments available for measuring how dark energy behaves. By measuring how fast voids expand and comparing the results to theoretical predictions, scientists can test whether dark energy acts as a constant or changes over time. If dark energy was weaker in the past and stronger now, voids would have grown slowly at first and then accelerated. If dark energy has been constant throughout cosmic history, voids should have grown at a steady, accelerating pace determined by that constant value. Observations of voids at different distances, which correspond to different times in the past, allow testing these scenarios. Another approach involves measuring the shapes of voids. If dark energy is truly uniform, voids should expand equally in all directions, remaining roughly spherical. But if dark energy has spatial variations, or if there are additional unknown forces at play, voids might expand more in some directions than others, becoming elongated or distorted. Observations of void shapes can therefore reveal whether dark energy has structure or is perfectly smooth. Current measurements, drawn from surveys like the Sloan Digital Sky Survey and the Baryon Oscillation Spectroscopic Survey, or BOSS, suggest that most large voids are roughly spherical and that dark energy has been approximately constant over the past several billion years. These results are consistent with the simplest models, the cosmological constant interpretation. But the measurements are not yet precise enough to rule out small variations. The Dark Energy Spectroscopic Instrument, or DESI, is already changing this. DESI began operations in 2021 at the Nicholas U. Mayall Telescope at Kitt Peak National Observatory in Arizona. It is designed to measure the redshifts of tens of millions of galaxies and quasars over a 5-year survey, creating the most detailed three-dimensional map of the universe ever constructed. As the DESI collaboration describes their mission, by mapping the distribution of galaxies and the expansion history of the universe over the past 11 billion years, DESI will provide unprecedented constraints on the nature of dark energy. Early results from DESI, released in 2024, hinted at possible time variation in dark energy, a tantalizing but preliminary finding that generated enormous excitement in the cosmological community. If confirmed by further data, it would be one of the most important discoveries in the history of physics, ruling out the cosmological constant and requiring entirely new theories for the nature of dark energy. The KBC void, being the largest and closest supervoid, offers the best opportunity for detailed dark energy studies. Its proximity allows measurements of unprecedented precision, probing the expansion rate and velocity field within the void at a level of detail impossible for distant voids. Whether it reveals a constant dark energy or a dynamic one, the void is proving to be an essential tool for confronting one of the deepest mysteries in science. As the cosmologist Saul Perlmutter, who shared the 2011 Nobel Prize for the discovery of dark energy, has reflected, "We discovered that the universe is accelerating, but we still do not know why. The nature of dark energy is the most important unsolved problem in physics. The void may help us solve it. Take a breath, let the mystery sit with you." Part 12. What if Einstein was not entirely right? The standard theory of gravity is Albert Einstein's general theory of relativity. published in 1915. It has passed every test thrown at it for more than a century. It predicted the bending of starlight around the sun, confirmed by Arthur Eddington's famous solar eclipse expedition of 1919. It predicted the existence of gravitational waves, ripples in the fabric of space-time, confirmed by the Laser Interferometer Gravitational Wave Observatory, or LIGO, in 2015 when it detected the merger of two black holes 1.3 billion light-years away. It predicted the precise shape and size of the shadow cast by a black hole's event horizon, confirmed by the Event Horizon Telescope's image of the supermassive black hole in the galaxy M87 in 2019. As the physicist John Archibald Wheeler, who coined the term black hole, once described it, space-time tells matter how to move, matter tells space-time how to curve. General relativity is, by any measure, one of the most thoroughly verified and successful theories in the history of science. But the KBC void challenges this foundation in unexpected ways. If the void is too large and too deep to arise naturally in simulations based on general relativity and lambda CDM, perhaps gravity does not work exactly as Einstein predicted on the largest scales. Perhaps the equations that describe gravity so exquisitely in the solar system, around black holes and across galaxy clusters, break down or require modification when applied to the vast, empty expanses of cosmic voids. This is not as radical as it sounds. General relativity has been tested primarily in regions of relatively strong gravitational fields near massive objects like stars, neutron stars, and black holes. In voids, gravitational fields are extraordinarily weak, far weaker than anywhere the theory has been precisely tested. It is possible, even plausible, that gravity behaves differently in these extreme, low acceleration environments. The most prominent alternative gravity theory is modified Newtonian dynamics, or MOND, proposed in 1983 by the physicist Mordechai Milgrom of the Weizmann Institute of Science in Israel. MOND suggests that gravity behaves differently when accelerations are extremely small, below a certain threshold of approximately 1.2 times 10 to the negative 10 meters per second squared. Above this threshold, gravity follows Newton's laws and Einstein's corrections exactly. Below it, gravity becomes stronger than general relativity predicts. MOND was originally proposed to explain a different puzzle, the rotation curves of galaxies. Galaxies spin faster at their edges than the visible matter alone can account for. Either there is invisible dark matter providing extra gravitational pull, or gravity itself is stronger at large distances than expected. MOND takes the latter approach. In the context of cosmic structure formation, MOND has an interesting consequence. Because it enhances gravity on large scales, it produces more vigorous structure formation than standard gravity. Superclusters become richer, filaments become denser, and voids become larger and deeper. Computer simulations using MOND-like gravity naturally create voids as large as the KBC void without requiring unusual initial conditions. The statistical improbability disappears. The void becomes an expected consequence of how structure forms under modified gravity. As Milgrom has argued, the challenges posed by cosmic structure, including the existence of unexpectedly large voids and superclusters, may be natural consequences of modified dynamics rather than anomalies requiring exotic explanations. However, MOND faces serious challenges of its own. It struggles to explain the temperature fluctuations in the cosmic microwave background, which standard cosmology with general relativity explains beautifully. It cannot easily account for the gravitational lensing observed around massive galaxy clusters, where the bending of light from background galaxies requires more gravitational mass than visible matter alone provides, strongly suggesting the existence of dark matter. Some researchers have developed hybrid models combining MOND with a small amount of dark matter, typically in the form of neutrinos, which can address some of these challenges while retaining MOND's advantages for structure formation. Another class of modified gravity theories involves changing how gravity propagates over large distances rather than altering its strength at low accelerations. These theories introduce additional gravitational fields or higher dimensional effects that modify gravitational dynamics on cosmological scales while preserving general relativity's successes on smaller scales. Some predict that gravity becomes effectively stronger in low-density regions like voids, which would make large voids easier to form. Others predict subtle deviations in the growth rate of structure that could be tested with precise measurements of galaxy clustering and bulk flows. Testing modified gravity requires comparing predictions to observations in the environments where the modifications matter most. Voids, with their extremely weak gravitational fields, are the natural proving ground. If the velocity patterns of galaxies within and around voids deviate from general relativity's predictions in specific, theoretically motivated ways, it could indicate that gravity needs revision. The debate between modified gravity and standard cosmology remains one of the liveliest in modern physics. Proponents of modified gravity argue that repeatedly finding structures that are too large or too rare, according to standard models, indicates that the models are wrong. They point to the KBC void, the Shapley supercluster, the Sloan Great Wall, and other enormous features as evidence that structure formation is more vigorous than lambda CDM predicts. Defenders of standard cosmology argue that modified gravity theories have their own problems, and that invoking them to solve one puzzle often creates new puzzles elsewhere. They prefer to accept that we live in an unusual location, rather than overthrowing a century of successful gravitational physics. As Einstein himself once cautioned, a theory should be as simple as possible, but no simpler. The question is whether lambda, CDM, with general relativity is too simple for the universe we actually inhabit. Take a breath. Let the tension between these ideas hold you. The universe does not care about our preference for simplicity. It is what it is. Our task is to describe it faithfully, even when that description becomes uncomfortable. Part 13. Are we trapped inside a bubble of false measurements? The term Hubble bubble has emerged in recent years to describe a troubling observational pattern that ties together many of the threads we have explored tonight. When astronomers measure the Hubble constant using nearby objects, supernovae, Cepheids, and other distance indicators within about 2 billion light-years, they consistently get higher values, around 73 kilometers per second per megaparsec. When they use objects farther than 2 billion light-years, or rely on cosmic microwave background data that probes the universe at much earlier epochs, they consistently get lower values, around 67 kilometers per second per megaparsec. The boundary between these two regimes, at roughly 2 billion light-years, is suspiciously close to the edge of the KBC void. This coincidence has led a growing number of researchers to propose that measurements made within the void are systematically affected by its presence, creating a bubble of biased observations. Only by looking beyond the bubble, beyond the void's edge, can we see the universe's true expansion rate. The hypothesis makes a specific, testable prediction. The measured Hubble constant should vary with distance. Nearby measurements should show the highest values, inflated by the void's outflow velocity field. As you look farther out, approaching and crossing the void's edge, the measured value should decline toward the cosmic average. Beyond 2 billion light-years, it should stabilize at the lower, true value. Recent observations are beginning to show exactly this pattern. Studies using Type 1, a supernovae at various distances, find that the inferred Hubble constant decreases with redshift. The trend is not yet definitive. The uncertainties at large distances are substantial, but the direction matches the prediction. As the cosmologist Lucas Lombreiser of the University of Geneva has written, a local underdensity consistent with the KBC void can naturally explain the apparent variation of the Hubble, constant with distance without requiring new physics. If the Hubble bubble is real, it creates a profound problem for observational cosmology. Our most precise measurements of the local expansion rate necessarily use nearby objects, because those are the only ones we can observe in sufficient detail. Distant objects are fainter, harder to characterize, and subject to larger uncertainties. This means our most reliable local measurements are exactly the ones most affected by the void. We are trapped inside the bubble, unable to step outside our local environment to see the universe as it truly is. It is like trying to determine the average temperature of the Earth by measuring only inside a heated building. Your measurements might be extraordinarily precise. Your thermometers might be the best ever made. But the numbers do not represent the global average, because your observing location is biased. Breaking out of the bubble requires observing objects beyond 2 billion light-years with comparable precision to nearby objects. This is technologically challenging, but becoming increasingly possible. NASA's James Webb Space Telescope, launched in December 2021, can observe distant supernovae and Cepheid variable stars with unprecedented clarity and sensitivity. Ground-based observatories with mirrors 30 meters across, like the 30-meter telescope and the extremely large telescope being constructed by the European Southern Observatory in Chile, will discover and characterize luminous objects at extreme distances. These distant probes offer a window into the universe outside the bubble. Early results are intriguing. Some studies suggest that the far universe expands at the rate predicted by the cosmic microwave background, consistent with the bubble hypothesis. But the data are still limited and subject to debate. More observations are needed before the trend can be confirmed with the statistical rigor that physics demands. The bubble concept extends beyond the Hubble constant. Bulk flow measurements show significant galaxy motions out to about 300 million light-years, but appear to decline at larger distances, consistent with the void, creating a local velocity field that dissipates as you approach the void's edge. Baryon acoustic oscillation measurements show discrepancies primarily at low redshift, again suggesting local effects. Multiple independent lines of evidence point to the same conclusion. Our local environment within approximately 2 billion light-years differs systematically from the universe at large. Accepting the Hubble bubble requires accepting something that is deeply uncomfortable for scientists. It requires accepting that many of the measurements we use to understand the universe are biased by our cosmic location. It requires accepting that Earth, despite centuries of decentering, occupies a position that is unusual enough to distort our view of cosmic properties. And it requires accepting that the numbers we have published in textbooks and taught in universities for decades may need revision. As the astronomer Wendy Friedman of the University of Chicago, who has spent decades refining measurements of the Hubble constant, has reflected, we must be open to the possibility that our local environment is not representative of the universe as a whole. That is not a failure of science. It is a call to measure more carefully and to look farther. Take a slow breath here. The idea that we might be trapped inside a bubble of biased measurements is unsettling. But it is also, in a way, beautiful. It means the universe still has surprises for us. It means there is more to discover. And it means that the act of looking farther, of pushing our instruments and our understanding beyond the boundaries of the known, is not just a scientific exercise, it is a fundamental human necessity. Part 14. What will the void become? Dark energy is accelerating the expansion of the universe, And that acceleration has implications for the far future that are both inescapable and deeply sobering. As space expands faster over time, structures that are not gravitationally bound together will drift apart and eventually lose all causal contact. This process is already happening. Galaxy clusters that are not part of the same gravitationally bound system are receding from one another, the distances between them growing year by year. But the process will intensify over the coming billions and trillions of years, and voids will be at the center of it. Voids will expand faster than the universe as a whole, because they contain less matter to resist the expansion. The filaments surrounding voids will thin out as the galaxies within them are stretched farther apart. Eventually, even neighboring superclusters will lose causal contact as the space between them expands faster than light can cross it. The universe's fate, if dark energy continues as a cosmological constant, is increasing isolation. Structures will become islands separated by ever-expanding voids. For galaxies within voids, this isolation will be profound. Currently, galaxies in the KBC void can still see the surrounding filaments and clusters in the distance. Light from those structures reaches us after traveling for billions of years. But as dark energy drives accelerating expansion, light from increasingly distant objects will be redshifted beyond detectability. The cosmic horizon, the boundary beyond which light cannot reach us before the universe expands too much, will shrink over time. Objects currently visible will fade from view. The cosmic microwave background, that faint afterglow of the Big Bang that has been so essential to our understanding of cosmology, will become cooler and dimmer as its photons stretch to ever longer wavelengths. Eventually, it will become undetectable by any conceivable instrument. As the physicists Lawrence Krauss and Robert Scherer explored in a remarkable paper published in 2007 titled "The Return of a Static Universe and the End of Cosmology," they demonstrated that a future civilization arising billions of years from now would find itself in a universe that appears static, empty, and devoid of the evidence that led us to discover the Big Bang, cosmic expansion, and dark energy. As they wrote, "We are living in a very special time in the evolution of the universe, the time at which we can observe the defining feature of our universe." This is a haunting thought. The evidence for the Big Bang, for cosmic expansion, for dark energy, for the cosmic web itself, all of it is visible to us now, in this epoch. But it will not be visible forever. The universe is gradually erasing the evidence of its own history. Within our own void, the long-term future follows this pattern with particular intensity. The Milky Way and Andromeda will merge in approximately 4 to 5 billion years, forming a giant elliptical galaxy sometimes called Milkdromeda or Milkomeda. This merged galaxy will be the dominant structure in our local group, but the local group itself will become increasingly isolated as other nearby groups, including the Virgo cluster, recede beyond the cosmic horizon over tens of billions of years. Milkomeda will eventually find itself essentially alone in an expanding void, a single galaxy surrounded by an ever-growing ocean of emptiness. Star formation will gradually cease as gas is consumed or expelled. The galaxy will fade, its stellar population aging from brilliant blue main-sequence stars to dim red dwarfs, and eventually to white dwarfs, neutron stars, and black holes. The night sky will darken. On timescales of trillions of years, even the longest-lived red dwarf stars will exhaust their hydrogen fuel and wink out. On even longer timescales, stellar remnants will slowly evaporate from galaxies through gravitational interactions, a process called dynamical relaxation. Black holes will grow by accreting whatever material remains. Eventually, even the supermassive black holes at galaxy centers will evaporate through Hawking radiation, The quantum process predicted by Stephen Hawking in 1974, by which black holes slowly lose mass and energy over incomprehensibly long timescales. A black hole with the mass of the Sun would take approximately 10 to the 67th years to evaporate. A supermassive black hole might take 10 to the 100th years, a number so large that writing it out in standard notation would require a 1 followed by 100 zeros. The final state of the universe, if dark energy persists as a cosmological constant, will be a diffuse sea of particles and radiation, expanding forever into darkness. Voids will have consumed everything. The last remnants of structure will have dissipated into the void's infinite expanse. As the physicist Brian Cox has described this far future, eventually, every structure in the universe, every star, every galaxy, every cluster will be taken apart by the expansion of space, and the universe will be nothing but a vast, cold, empty void. That is the ultimate fate of everything. This future is billions of years away. It depends on dark energy continuing to drive accelerating expansion, which current observations support, but it is, as far as our best physics can determine, inevitable. The cosmic web we observe today, with its intricate filaments and blazing clusters, is a temporary phase. The true long-term structure of the universe is emptiness. We live in an unusual time, a brief window in cosmic history when the universe still has rich structure, when voids are features rather than the dominant reality. Billions of years hence, voids will be everything. Take a slow breath. Let the weight of deep time pass through you. You exist in a precious moment. The universe is still structured. The sky is still full of stars. The cosmic microwave background is still detectable. The evidence of the Big Bang is still written across the sky. None of this will last forever, but it is here now, and you are here to witness it. There is one final question. If we live inside a cosmic void, are there other civilizations elsewhere in the cosmos, inside their own voids, asking the same questions we are? The distribution of matter in the universe influences where life can emerge. Galaxies need sufficient heavy elements, carbon, oxygen, nitrogen, iron, to form rocky planets capable of supporting complex chemistry. Those elements are created by stars through nuclear fusion and scattered into space by supernovae. In dense regions of the cosmic web, star formation is vigorous and heavy elements are abundant, but dense regions are also dangerous. Nearby supernovae and gamma-ray bursts could sterilize planets within thousands of light years. Active galactic nuclei in cluster galaxies pump enormous energy into their surroundings, potentially disrupting planet formation and habitability. Voids offer a quieter alternative. Galaxies and voids evolve peacefully, forming stars at a moderate pace, providing billions of years of stability. Catastrophic events are rare. The isolation provides long-term protection from the violence of dense environments. As the astrobiologist Milan Cirkovic has suggested, galactic habitable zones may extend beyond individual galaxies to encompass the large-scale structure of the cosmos, with void environments potentially offering advantages for the long-term survival of biospheres. If other civilizations exist in voids, they would face the same cosmological puzzles we do. They would measure a local expansion rate that might not match the cosmic average. They would observe bulk flows driven by their void's gravitational imbalance. They would wonder, as we do, whether their measurements are biased by their location. A civilization deep inside a void, billions of years from now, after the cosmic horizon has shrunk and the evidence of the Big Bang has faded, would face an even stranger situation. Their sky would be nearly empty. There would be no distant galaxies to observe, no cosmic microwave background to measure, no evidence that the universe was ever anything other than a small, static island of stars surrounded by infinite darkness. They might conclude, quite reasonably, that their galaxy was the entire universe. They would never know about the cosmic web, the Big Bang, or the expansion of space. They would be wrong, but they would have no way to know it. This raises a question that should unsettle every cosmologist alive today. Is the same thing happening to us? Are there truths about the universe that we cannot see from inside our void? Are there measurements we are making that are biased in ways we have not yet identified? Is there a larger reality beyond the KBC void that would change everything we think we know? As the physicist Carl Sagan once wrote, somewhere, something incredible is waiting to be known. Perhaps the most incredible thing waiting to be known is the answer to whether our understanding of the cosmos is limited by the accident of where we live. We are inside a cosmic hole 2 billion light years wide. This is not metaphor. This is not speculation. This is observation, confirmed by multiple independent studies, consistent across different datasets and techniques. The KBC void is real. Its effects are measurable. Its existence challenges fundamental assumptions about the homogeneity of the universe, the accuracy of our expansion measurements, the statistical predictions of the Standard Model, and the nature of gravity itself. Whether the void fully explains the Hubble tension, whether it requires modified gravity, whether it makes us unusually positioned in the cosmos, these questions remain open. They are among the most important questions in physics today, and they will be answered eventually by future telescopes, future surveys, and future generations of scientists who inherit the mystery we have explored tonight. But one thing is certain: the universe is far stranger than we imagined, and our place within it is more unusual than we ever suspected. We are cosmic castaways, drifting through a desert of space, measuring a universe that may not be what it seems. And yet, here we are, aware of the void, aware of the bias, aware of the questions, and still looking outward, still searching, still asking. As the astronomer Carl Sagan said in one of his most enduring reflections, "For small creatures such as we, the vastness is bearable only through love. Perhaps it is also bearable through curiosity, through the stubborn, beautiful human impulse to understand, through the willingness to sit in the dark and ask questions whose answers may take generations to find." Thank you for being here tonight. Thank you for listening. Thank you for carrying these questions with you into the quiet hours ahead. If this journey meant something to you, a gentle like, a quiet tap on subscribe, or even just a moment of silence in which you let the cosmos hold you, that would mean the world to me. Every bit of your support helps others find their way here. And your words, your presence, even your silence, they are like little stars in the dark. Tell me where you are listening from tonight. I would love to know. Leave a quiet word in the comments if you feel like it. And if you are ready for more, another journey is waiting for you on the screen right now. Until next time, may the universe turn softly around you. Good night.